Okay, just a moment. Yes. Yeah. Okay. So good afternoon, everybody, and good evening, Clemency.
Thank you.
You are our second guest speaker for the camp. We just finished one, and I'll just take this opportunity to introduce Clemency in a very short and sweet way. So Professor Clemency Montelle is a professor at School of Mathematics and Statistics in the University of Canterbury in New Zealand, and she holds a first class honors undergraduate degree with a double major in mathematics and classical studies. So this is a very unique combination. There are very few people who have this kind of background, and she has a good hold in several languages, including Sanskrit, Greek, Latin, and I don't know, many more. So she has done her research from the Brown University in US, and she has worked under some eminent historians like David Pingree and Kim Plofker, and these are names that you will hear when you start reading about history of mathematics. And she's on board on several organizations related to history and mathematics, and she's a well-known figure all over the world when it comes to history of mathematics. In fact, she frequently used to visit India before this COVID thing happened, and she that's where I met I met Professor Clemency in a workshop at IIT Bombay. So she's a very sought out after person. She's a researcher I would say in her head, but she's a teacher at her heart. And you can see the passion that she drives into the session when she does that. So I'm very happy, and I feel that all of us are very lucky to have got you here for this session. Thank you so much for joining us for this session, Professor Clemency Montelle. I'll hand it over to you. Would you like to just share, somewhere in between, would you like to just share how you fell in love with this thing about history of mathematics?
Absolutely. So thank you very much for inviting me, and I'm really delighted to be here, and I hope that I'll be able to travel to India very soon and we can run more sessions like this, but we can actually be face-to-face in person, because it's much more fun learning and sharing ideas when you're not separated by screens, although it's the next best thing, right? So I will put my screen on, and I will, let me just see if I can get back to where oh dear, I've lost it. Hang on a minute. Here we go.
And if they have any questions, they can just do a raise hand, and then we'll unmute them and they can ask questions, right?
Absolutely. So what I'll try to do with Mr. Vinay is try and make this session quite interactive. So I'm going to throw out stuff. We're going to try and explore it together, which will mean a little bit of discipline on our part for putting up our hands and yelling out the answers. But let's see how it goes. And, if it doesn't work, then we'll try another technique. But I'm hoping to be as involved as possible with all of you, because the best way to learn something is to actually discover it for yourself rather than just listen to me tell you what it is. But before we go into some stuff which looks like mathematics, or at least I've assured you that it looks like mathematics, I'm going to share for you a photo that I don't share with very many people, but I promise, I think you'll be the audience who will look at it. And this is a photo of me when I was 14 years old. So probably the mean age of all of you now.
Sorry to interrupt. We can't see that photo.
Oh, hold on, it's coming.
Oh, I see.
Aha. So not many people get to see this photo, so you're very privileged here. So this was me at 14 years old, and really you can see I've got the most incredibly large pink glasses, which I think I still have in a drawer somewhere, but I thought it was they were wonderful, even though everybody teases me now about them. So anyway, so this is me as a 14-year-old. I'm probably about close to your age, and I really loved mathematics at school, and I really liked learning French, and I did some Latin after school, and and you just really enjoyed these two different language type subjects and mathematical type subjects. And you can see, I'll show you, in fact, you can play a guessing game. Can you see me? Here's my class. We call it year 10. So all of my friends, you can spot me if you just look for the pink glasses, right? Who can see me? Aha, I'm the only one with glasses in the entire class. So there you have me, a 14-year-old, loving mathematics, loving languages, loving the humanities, loving history, loving classical studies, happily pursuing these things at school. And in a very, I look at some of the other students, some were into biology, some were into chemistry, some now own restaurants, some now own businesses, some have gone overseas and are working on the stock exchange. But here was me right here, loving languages and loving mathematics. And in fact, what this led to is me to go to university and to have what is actually being called by scholars, the two cultures. And in fact, so here's mathematics on the one hand, and here's my languages on the other. So I learned some, living languages, but my passion really was learning ancient languages. Sometimes we call them dead languages because the people that speak them are no longer around anymore. And typically they're very old and very interesting. So this is ancient Greek and math. So the two cultures. And these two cultures, I really wondered for the longest time how I could bring them together, but I continued to study them quite separately until I realized I could put them together. And how could I put them together? I could read ancient mathematical texts in these languages and try and figure out what they mean. And I thought, this is what I want to do. This is just absolutely fascinating to me. So here's a copy. Some of you might have heard of a very old Greek mathematician who flourished in about 300 BCE, it's thought, whose name is Euclid, and he wrote a very famous geometry textbook called The Elements, of which here's a Latin copy here. So the real appeal to read ancient mathematics in these languages was something that really, really was my passion. So as Vinay mentioned, I went to do a PhD in this. I decided this is what I wanted to do, and went to Brown University in the United States, which is in Rhode Island on the East Coast, and worked with his very famous scholar, Professor David Pingree. And you see this empty chair here? This is where I sat, and we would sit here and read ancient mathematical texts and try and figure out what they mean. And it wasn't just in Greek, but Professor Pingree introduced me to Arabic, to cuneiform, as well as Greek and Latin, and of course Sanskrit, which is a language which is very familiar to you. All you might have even learnt some in school, will be learning some currently, or be able to read Nagari at least. And so that's the basis of my research, and that's where it started, very much in this room here, in this really, really privileged, beautiful apprenticeship that I had with this very, very talented expert. And so these two cultures, of course, some of you too will be drawn. And in fact, the two cultures, the idea of the two cultures, we've got Einstein here on the left, and we've got Shakespeare here on the right. You might have read some of Shakespeare's plays. You might have tried to read some of Einstein's stuff, I don't know. And little Cupid or a little Karma, individual here that's shooting both arrows into them. So how do we blend, how do we humanize mathematics, or how do we treat the humanities a little more scientifically? In fact, it's becoming more and more relevant, as you will find in every day, that mathematicians have to communicate, and likewise the humanities have to confront the sciences when they're doing it. So very much think about where are the two cultures in your life, and the wonderful things that you can get when you bring these together and make insights. So I've told you, and I feel very, very proud of this picture, and this is why India is my second home, that my navigation to the two cultures led me to my real love, which is Sanskrit, and of course many visits to India. And bringing my children along, of course, as well, because so I feel like I deserve somewhat of, you know, some sort of permanent residency, because I can fit all my children on a motorbike and take them around the city, of course. In fact, there's room for another one there, right? There's a big space in the front. So so what I do is I've been traveling around India when I visit, and actually going to amazing repositories of manuscripts. Here's the manuscript library at the wonderful University of Madras in Chennai, for those of you who are in Chennai, which is filled with manuscripts, and they're written in Sanskrit, they're written in Malayalam, they're written in Bengali, they're written in Tamil, all sorts of languages that you can imagine. And they're sitting there waiting to be read. So this is your direct intellectual heritage in these libraries. And of course, estimates are that there are at least 30 million, or maybe as many as I should say, 30 million manuscripts of some sort that are in India currently in these manuscript libraries waiting to be read and documented, which is a very exciting prospect indeed. And probably, I mean, a lot of these are epics of the Mahabharata or the Ramayana, or their legal texts, or their, you know, historical texts, or have you, but probably around 10% of these are scientific. So they're astronomy, they're mathematics, they're everything in between. And here's this beautiful, so this is a palm leaf manuscript here. You can see it's an astronomical one. You can see there's a little astronomical diagram here. And I think the script here, somebody might be able to correct me, but this is looking very much like Tamil, or maybe even Malayalam. Indeed, so this is and you can see it's written on palm leaf, so it's quite fragile but robust and has lasted for a while. And the way in which they would bind these manuscripts was to be put little holes through the center and bind them up with a ribbon or a string there, and put them between two boards. So really, in Sanskrit cultures alone, they're, you know, lifetimes worth of work. So, you know, people have manuscripts in private collections. You'll find them in libraries around your cities and all places. It's really important. This is your direct heritage, and some of it's mathematical as well. So there's lots to be discovered here.
Looks like we have a question. You want to take it now?
Yeah, please.
Arav?
Yes, ma'am. Ma'am, as you said that you had an interest in language as well as mathematics.
Yes.
But ma'am, language is actually when you imagine something. Language is all about imagination. It is about fantasy and all. And mathematics is actually proving things. Mathematics is not fantasy. It is proving things and also sort of scientific stuff. So did you like face any challenges combining these two subjects and like turning this into your passion? Did you face any challenges?
Indeed, but you know, what is a proof, right? You have to have this wonderful imagination as a mathematician, right? You've got to discover things and relations that don't even exist yet. You know, mathematicians, the best mathematicians, have fireworks going off in their head because they're so intensely creative. So in many ways, I think you're right. Mathematics requires a certain analytical discipline, you know, careful with your symbolism, careful with your logic, but it also requires an intense amount of creativity. So I think your point is really, really very, very profound. But I would say the very skills that you need to be a good student in the humanities, you also need to transfer in mathematics. But you're right. Any discipline which is sort of takes two disciplines, you know, if you're doing, I don't know, you know, history of medicine, or you're doing, you know, digital humanities or something, requires you to be an expert in both disciplines. So you've got sort of two audiences to satisfy. So it's a very, very interesting question. Yeah. So very many challenges. Yes.
Clemency,
Vinay,
would you like to take questions like these now, or would you like to keep questions like this towards the end?
I might keep questions like this towards the end. This is sort of the icebreaker, so you get to know, and I'll get onto some maths, and then we will maybe take some more general questions at the end. What do you think? Yeah.
Sure.
So,
Raghav, you have anything related like this? Then we can keep it towards the end, or if it is something to do with whatever she has discussed so far, we can take it now. Yeah.
Yes, sir. So language is all about literature. It's all about imagination and freedom. But when it comes to mathematics, you cannot think anything of your own, and you have to relate to the existing principles. So, what is the secret behind integration of these so many languages with mathematics?
Yeah. Well, I would say, actually, if you look at Sanskrit, which is a very heavily inflected language, all right, and it was codified early in the first millennium BC by an individual called Panini, and he started by doing a phonological analysis of the language. So you start with all the sounds that you can make, and then how you put those sounds together to make syllables, and then how you put those syllables together to make words, and then how you apply rules of grammar to make sentences, and then how you apply the rules of prosody and poetry to put those sentences together to make literature. So in fact, Sanskrit has this incredible mathematical approach to one of their primary languages that's spoken on the continent. So I would argue, in fact, that many analytic, careful, logical rules that you think of the domain of mathematics, you can find in languages as well. And the further back you go, the more heavily inflected languages tend to be. They follow very strict rules in terms of what you can do and what you can't do. So there's some intersection there, which I think is very interesting. And in fact, one of the interesting observations about early Sanskrit mathematics is they didn't have anybody like Euclid who set out to do proofs of things and set out the essentials of geometry, like what is a line, what is a point, what is a plane. But I would say, look not in mathematics, but look in linguistics and ancient Indian culture. You will find the deduction principles that instead you don't find in mathematics, but you will find in linguistics. So it's a very, very interesting question that you have. And I would argue that in fact, language and literature actually has its own rules as well. Right, so we will push on and actually look at some mathematics now. So there we go. This is my introduction to some of the history of mathematics that's probably closer to your doorstep. But what I want to do now is go to the world's oldest mathematical culture, and that is the mathematics of the ancient Near East. And we'll have a little bit of a look at where I mean geographically in a minute, but what I want to do is just throw you in the deep end, because I know how all of you love a challenge, and start looking at an ancient mathematical text. Now, what I want you to do is you can either look at your screen, or you can perhaps get the PDF that's on the SharePoint site. But what I want you to do is have a very close look at this. So you can imagine, I'll just set a scenario for you. An archaeologist has run up and they've dug this out of the ground. It is a cuneiform tablet. So it's a sort of a something that's made out of clay. It's very rough and heavy. It's got two sides. So we've got one side here, which we're calling the obverse. And on the other side, so this is one object, but it's got two sides, just a little bit like a coin. And just like coins, you call it the obverse and the reverse, or the recto and the verso. We're doing the same thing here. So the reverse is here. Now, I'm going to tell you it's mathematics, but of course it's looking pretty foreign to you now, right? So what I want you to do is just familiarize your eyes with this and have a look, see what you can see. We've got, as this person as this historian has written, we've got two columns on each side. So I want you to read down each column and see if you can notice some patterns. And Vinay, I'm going to rely on you just to choose some people who want to venture into this.
Okay.
Yeah.
So maybe I would like to give 30 seconds for them to observe so that everybody gets some fair time. And if you see some patterns, you can just do a raise hand and I'll call out your names.
Yeah.
Looks like they have decoded everything, Clemency.
That's great. I've got some harder stuff.
Okay, let's see what maybe Venkat has got. Venkat.
Ma'am, I think they are numbers.
Okay, so tell me.
Like that's 1, and then when you keep 2 ones together, you get 2, and then you go all the way up to 10.
Okay, so I've got
like
1.
Roman numbers.
Yep. Okay, so very, very good. So we've got 1, and we've got 2, and we've got 3, right? And now look, what have we got now? What do we expect, Denkant?
They have 3 on top of a 1, so it becomes a 4.
Okay, brilliant. So that's
And
the
then
lovely
3 on
thing.
top of 2 becomes a 5.
That's right. Excellent. Yep. And then 3 and 3 becomes a 6. And then without looking at the next one, what do you think is going to happen?
Then we get 3 and 3 and 3, we get 9, and then the next one is a 10.
Okay. Well, wait a minute. We've got to get to, we've gone from 6. Where are we going after 6?
Then 3, 3, 1.
Yep. So you see that wee one stuck in there in the bottom. Yep.
Then 3, 3, 2, and then that's
Yep.
8. Then we have
Yep.
3, 3, 3, we get 9.
Yeah. And then what do we want next? We know what this
10.
has to be. 10. All right. And after 10, we've got
11. We combined a 1 and a 10.
okay, we combine the one, and then we've got 12 and we've got 13. And then just like we expect the person that wrote this, that we sometimes call him the scribe, the person that wrote this has thought the system for writing numbers is you get 3 and then that's just too much and you slip down the bottom, right? So we've got up to 14. All right, now I want you to take 30 seconds. Now that you think you know what this says and now you know something about numbers, what is this column? Right, you've got 30 seconds. I'm timing you.
Yeah, you're asking for column number 2, right?
Yeah, so give 30 seconds. Don't just say, you know, just go down and check.
Shall we ask them to put their answers in the chat, or you want them to speak?
What do you think will work best? Maybe somebody can speak.
Okay, so maybe Vansh Patel. Vansh, can you unmute? Yeah.
Okay, yeah, so like I think this is like in the column to the first thing that I see is like it is 3 and like it is 3 below it and again 3. So
Yep.
like it is like that, a table of 3.
Okay.
Okay. Yep.
Maybe.
So what,
Yeah.
yeah.
Sorry. You were saying something.
So what number do we have? If this is a number, what number will it be?
Tanmay?
9. I've got sign language going on. This is fantastic. All right. So
the multiplication table of 9.
Okay, a multiplication table of 9. Excellent. So we've got 1 and then we've got 9. Now what have we got underneath? What would we expect?
Parth?
Yes, so we'll get 18 and 27.
Okay, so we've got 18 here. Very, very good. All right, so it looks like we've got a multiplication by 9. So we've got 1 and 9 next to it. 2 times 9 is 18. Good. 3 times 9 is 27. 4 times 9 is 36. So you can see what happens is we just collect these sort of funny wedge-shaped symbols like this. These are the 10s and these are the 1s. All right, we're feeling pretty confident. You think, oh, Clemency, come on, let's go to the next one. So 4 9s are 36, 5 9s are 45. See how they kind of group them in? Remember, this is a human being, not a computer doing this, so don't expect them to be neat. If I was going to look at your textbooks, I bet, you know, it wouldn't always be wonderfully neat. So 6 9s are 54. So we've got 1, 2, 3, 4, 5, and 4 here. 7 9s are 8 9s are.
You want them to say something about?
Please, who's got an idea? What's going on?
Yes, ma'am. Can you repeat which column?
Okay, so we were very happy, right? Everybody was very happy until it was 6 9s are 54, because our hypothesis is that this is a 9 times table. But when we get to 7, what's going on here?
Nandita?
They have given a different symbol for 60, 63.
Aha. All right, so we've gone up to 50 and then we've got a different, so what we know, this is the lovely thing about the logical consistency of mathematics, right? We know what it has to say. We need this somehow to say 63. So really what we're saying is 1 here, this must be the 60 and the 3 is here. Similarly, let's just keep with this hypothesis. So we've got, what was this again? 7. 8 9s are 72, right? So we've got a 6 and a 12, right? 9 9s are 81. So again, we'd have 160 and a 21. And then 10 9s are 90. So we've got a 1 for the 60 and 30 here, which will give us our 90. So you're entirely right. This is a multiplication table. It's the 9 times table, but it's not in base 10. What base is it in? Anybody? Somebody want to jump in the chat?
Jivitesh.
We've got it in.
I think.
Ma'am, I think in base 60.
This is in base 60. You're exactly right. And this is what we sometimes call sexagesimal. Base, vigesimal is base 20, decimal is base 10, sexagesimal is base 60. So in fact, this is a very interesting thing, and you can go through and check them all, right? So we've got 9 11s and so forth and so on. So from this tablet, and you can just zip through, particularly those of you that got really enthusiastic and keen, keep going and have a look, and you can check all of these things. We've got a cuneiform tablet that's giving you a 9 times table, but it's in base 60. So anytime you get confused, you just think this is like our hours and our minutes, okay? Just like we might say a movie is 1 hour, 3 minutes long, or otherwise known as 63 minutes. So very fascinatingly, the world's earliest mathematics started not in base 10, but in base 60. The very first earliest counting systems that we have started in base 60. So you can just zip along and see when it's 12, it's 148, when it's 13, 14, and so forth and so on to the next one. So you won't need to do that there, but just this is the 60 placeholder. Now, what's very, very interesting, so I'll just talk a little bit about this, and you can keep looking at the SharePoint site, the PDF if you want to keep working through it, is that this is a sort of a semi-positional or place value system. What I mean by that is that how did you know that this was a 1 and this, which is exactly the same symbol, was a 60? It's where you put it, but there's no decimal point, there's no sexagesimal point, there's no way to be able to tell successive sexagesimal places. It's just simply where you put it in the little space that you have that allows you, so it's almost like context that allows you to determine whether or not you read it as a 1 or a 60 or 1 over 60 or 3,600 or the like. But what's also very interesting about this is that we've got an embedded base 10 in here. So although we've got base 60, of course, base 60, a true base 60, you would actually need 59 distinct symbols to be able to count in it. So in base 10, we've got 9 different symbols plus a place holding 0. In base 60, in principle, you'd actually need 59 different symbols. Who can remember 59 different symbols, right? I mean, it's quite a lot. So in fact, what we do have, even though we've got the earliest form of counting we've got is base 60, we've got an embedded base 10 here. So you can see we've got 2 symbols to write any number that we want, 1 for 10 and 1 for 1. And we call these wedges, right? And we'll have a little look at how you actually do these for real. But there's one which is sort of an imprint like this, and there's a long vertical wedge that we see here. So some other really interesting points that I'll say about this, because actually from this little wee 9 times table that was probably written by a student, and I say that because, you could give me all the reasons, but you might like to think about the reasons is why I say it's probably a student copy. Well, look, it's kind of messy, right? Some of the wedges are different shapes and some of them are bunched together and some of them are, you know, squashed in. Also, look at the ruling of the lines. Come on, if you were a professional, would you rule your lines? You know, you do a better job. So, and not only that, but right here, you can see there's a wedge that's been made with a line through it. That's the way of erasing something. So the students made a, you know, the scribe who's written it's made a mistake. So probably say it's probably a student. Now, the interesting thing, so from this little 9 times table tablet, we can actually say quite a lot about what was it like to do mathematics in the ancient Near East. What was our very first mathematics that we did as human look like? So we can say it's base 60, but there was sort of a base 10 going on. The other thing we can say is goodness. Okay, you've picked up very quickly within seconds of looking at this, that this was a 9 times table, but do you see an equal sign? Do you see a multiplication symbol? Do you see anything? No, we've got no symbolism, but it was the context in which it was the patterns that told you how these were related, right? You picked it up very quickly, but that is another thing. There is no mathematical symbols for arithmetic like our addition symbol, subtraction symbol, multiplication, division, let alone X's and Y's and all the rest of it. So, but that didn't matter. So instead of having symbols, they used alignment. So we can see here's what's being multiplied and here's the answer. So this sort of alignment did the work of what our symbols do these days. Another very interesting point you can make is, right, so you know, when you first learnt multiplication, at least when I did at school, I learned up to 12 times table, right? I might have learned a bit more, but really probably only need to know up to 10. 12 is, I think, is left over from old currency. How many multiplication tables would you actually need to learn in base 60? Somebody just want to quickly yell out an answer?
I need to unmute them if they want to speak.
Yeah.
Okay.
How many multiplication tables?
Sorry, you went on mute. Can you just unmute yourself?
I'll repeat the question. Yeah. How
Yeah, sorry.
many multiplication tables would you need to learn as a young child if you had to do arithmetic in base 60?
59. 59, yeah.
59.
Ah, who's looking slightly stressed? Yeah, so you would
59.
need to, in principle, learn 59 different multiplication tables, all right? Because, you know, that's what you'd need to do. And in fact, so let's just go back here. Do you see 59 entries here? No, we don't. So what is the scribe done instead? We don't go from 1 up to 59. Let's have a wee look. So we go 15 at the bottom, sorry, 14 here at the bottom, 15 here, 15 times 9, 16 times 9, and you can figure these out for yourselves, 17 times 9, 18 times 9. Actually, this is the number for 19. It actually is written 20 minus 1, interestingly enough. Okay, so there's 19, and you can do that by times that by 9, and then you can convert it into base 60 to double check that the student scribe's done okay. And then we've got 20, and then we've got 30, and then we've got 40, and then we've got 50. All right, so basically, if you want to multiply, I don't know, 35 by 9, you just take the entry for 30, you'll take the entry for 9, you'll take the answers and you'll add them up. And that's so you don't have to carry around a massive cuneiform tablet that's got 59 different entries. And then you don't have to carry 59 of these around because this is, of course, in the days before iPhones when you could just pull out your electronically assisted brain and compute your multiplication tables for you. So there's another very interesting feature about base 60 and doing basic arithmetic.
Clemency, sorry, if I can interrupt.
Yes.
There were a few hands raised. So would you like to take questions now on
Please.
this?
Absolutely.
Okay. Whoever has any question, please do a raise hand and I'll call out your name. Omkar.
Yeah, so did they use base 60 because there were 60 seconds in a minute and 60 minutes in an hour?
That's a lovely insight. Flip that around. That there are 60 minutes in an hour and 60 seconds is definitely because our first system of numeration was base 60. So in fact, that we count time like that is because it was base 60. So that came afterwards. I've got some, nobody knows for sure why there was base 60. There are some ideas around there. And one of the ideas is that 60 is a number that has lots of divisors, right? 2, 3, 4, 5, 6, not 7, 8. Not quite 8 properly, and so forth and so on. So they think 60 might have been this really good number that had lots of divisors and was easy to do arithmetic to. So that's a very good question. But time, of which, so you can see, even 5,000 years later, we still have, you know, in our everyday life, traces, or at least, you know, really strong evidence of this very first number system that we use. That's a really good question.
Miss, was there like something like a sundial or some way to measure time in that age?
Absolutely.
Oh, right.
Yep. Very sophisticated time measurement. Yep. They could measure time down to seconds, in fact, and could time eclipses and other astronomical events to great precision. So there was very.
What will you say is the age when this was written approximately?
This particular tablet was probably around the middle of the second millennium BCE. So, you know, sort of minus 1,600 or 1,900, but there's no date on it. All right. We don't know who wrote it. We don't know where it came from or the like. So we can only guess. Yeah, but that's a very good question. So the beginning of writing of cuneiform started in around the middle of the sort of minus 3,500. That's when we have the very first cuneiform text and the very first expressions of writing. That's earlier than Egyptian hieroglyphics. Yeah.
Achyutan?
Ma'am?
Yeah, sorry, just 1 second. Guys, I would appreciate if you do a raise hand and wait for your turn. Shreyan, can you just wait, please, Achyutan?
Yeah, my question is, in the second row of the second column, how will we know if it's 18 or no, I think column 2 and entry number 2 of the first tablet.
Oh, here.
Yeah.
So that's 10. And so you see 1, 2, 3, 4, 5, 6, 7, 8.
Yeah. How will we know if it's 18 or if it's 608? Because
you don't. It's a very good observation. There is no absolute magnitude. It's all relative. But context will help supply the answer. For instance, if you went to a shop and something, you know, it had 100 on it, there was a t-shirt in a shop and it had 100 on it, you'd probably guess it's 100 rupees, not 100,000 rupees or like 100 paisa or whatever, you know?
Yeah.
And so that's exactly context. It seems very difficult for our mind not to be able to express an absolute magnitude of a number. It's really frightening, but they did it. And they were absolutely happy. In fact, it really doesn't matter. You could read that 18 as 18 times 60 if you wanted to, because the relative magnitudes of the numbers would be fine by that reading. But very good observation. And my answer is there is no way to express absolute magnitude. It's all contextually based. Vinay, shall I keep moving on?
Yes, please. Yes, please.
Ma'am, 1 minute, ma'am.
Okay,
yes.
guys.
Ma'am, in the second this one, ma'am, in the second manuscript, or what you call in the last one after 50, there is one number, ma'am. Like, what is that one?
Yes, ma'am. Even I wanted to ask the same thing.
Well, in this one here.
Ma'am, I think it's 59.
Yes, ma'am.
This one here. This is a very good question. So this is in fact what we call a catch line. So this relates to the fact that when I said how many multiplication tables would you need? So in essence, a school child would copy out a 2 times table, a 3 times table, a 4 times table. So they might, if you were a professional and you had to do arithmetic, you might carry around, you know, and literally these are about the size of your cell phone. It's really quite ironic. And so you might carry around a satchel with about 59 of these in it. And there's no page numbers or tablet numbers. The next best thing we've got is this. Now this says, in fact, 820 multiplied by 1 is 820. And this says, this means that the next multiplication table in the sequence is 820, okay? And so if you wanted to order your tablets, this is what we call a tagline or a catch line. It's saying the next tablet in the sequence, in fact, is the multiplication table for 820. All right, so it's a very, very good question. And then so the multiplication table for 820, which would be another tablet, would have another catch line which would tell you the multiplication table next for that. So an excellent question.
Okay. Clemency, I think you can move on. We have about 50 minutes.
That's right. On the SharePoint, on the PDF that I've circulated, there's another multiplication table for you to do, and it's an 8 times table, but I will warn you now, the scribe has made quite a few mistakes, so see if you can spot them. So that would be something you can leave for homework, and I can post the answers if you like later on. All right, so very quickly, I'll tell you where this tablet comes from. It's from a place called ancient Mesopotamia, which is sometimes called the Fertile Crescent, because you see this sort of looks like a moon shape between the Tigris River here and the Euphrates. And this is sort of an area which is roughly equivalent to modern day Iraq. And in fact, it was very, very attracted people because of the rivers and their ability to do agriculture. And with agriculture, with more proper agriculture came the need to trade. And the minute you start trading, you need to start writing stuff down. And the minute you need to start writing stuff down, you start doing mathematics. So this is where we're looking at. And these are literally found, archaeologists will unearth tablets like these, and they will go into the desert, and they will travel around until they get to these mounds. And these are the remains of ancient cities which have basically had sand doing them. So archaeologists literally can just dig down and they unearth these amazing cities and ruins with palaces and temples and libraries and marketplaces and private residences and schools which are full of multiplication tablets like the ones that we see. And so we didn't know anything about the civilization, amazingly, until about 150 years ago. And here's a cuneiform tablet here, which has got writing. So I won't make you read this one. It's not mathematical, but you can just see how absolutely beautiful it looks, and the precision of the writing here. But you'll be able to pick up the fact that we've got some vertical wedges here and some of those horizontal ones that you saw before. And of course, the technology of cuneiform is determined by what's around. This is before paper, this is before pens or quills or stylos or anything. Clay is in abundance next to these rivers, as is the reeds which you use to be able to write this stuff. And so you have a clay tablet here, which you hold in the palm of your hand. And you'll have the stylus here, which might be a reed from the river, and you will make the cuneiform signs. And we don't have time now, but there's a wonderful video on YouTube with Irvin Finkel, who is really a wonder to behold. He works at the British Museum, and you can see he's actually got a piece of clay, and he actually's got a stylus right here. And with these two individuals here, he shows you how to actually impress and write cuneiform just like they would have 5,000 years ago. So you can just go on YouTube and go Irvin Finkel and technology of writing and have a look. It's about 20 minutes long. It's very entertaining for those of you that are interested. And we won't labor a bit on it too much, but what we will see is, the beginning of writing, which is very pictographic at the start, but for some reason, all the signs rotate around 90 degrees and become more and more abstract as you go through time to get the very wedge shapes, the abstract wedge shapes that we see today. So one of you very astutely asked me why base 60, And in fact, it's a very interesting old system of alternating bases. And, you know, if we were working together, I would say, can you think of another system in which you get alternating bases? And of course, we got a very, very famous one that you'll be well familiar with, I think, which is Roman numerals, which are alternating bases of 2 and 5. Okay, so you've got symbols for 1, for 5, for 10, for 50, for 100, and so forth and so on. So we've got these symbols here, y base 60, that we've got evidence for that. You can see they started off being very elaborate. By the time we get to the late 3rd millennium, instead of having lots of different symbols for increasing orders of magnitude, we just have these 2 simple symbols that you've seen, 1 for 1, 1 for 10, and increasing orders of magnitude here. And remember, no absolute magnitude. A 1 can be a 1, it can be a 60, it can be a 3,600, and it can be a 1 over 60 and the like. So very, very interesting way of doing arithmetic without your beloved little decimal point. All right, here's a bit more of a challenge. Here's another numerical table. This one's got a bit more words. Now I want you to see if you can figure this one out for me. This should be a wee bit more challenging. Don't worry about this first line. Let's start here now. I'm just going to pull out, you can see there's a symbol at the start, which you will pull out. I'm going to tell you this is the cuneiform word for the word it's. I'll write this in the chat while you're having a look. So it's, then we've got a column of number. This nasty looking cuneiform symbol here means part. And then we've got another column of numbers. So what I want you to do is take, maybe I'll give you 2 or 3 minutes to just go down. So it's, and then we've got the number 3. It's 3 part 20. Okay, it's 3 part 20. And I want you to go down and see if you can spot a pattern and tell me what you think this tablet is, what relationship this is embodying mathematically. Right, you've got 2 minutes, go.
Naveen?
Sir, I got the answer.
You've got the answers?
Go ahead.
Tell me.
Sir, it's division.
Ah, tell me more.
Sir, it's 60 divided by 3, so they get 20. And then it's 60 divided by 4, they get 15. And then 60 by 5, 12, and so on.
Mm-hmm. And so that's absolutely right. So we seem to have these some sort of division table, right? Okay, so then we've got 6 and we've got 10. Why don't we have 7?
Because it's not perfectly
It's
divisible.
not divisible by 7.
Not perfectly divisible.
There you go. Now, so sometimes we say, actually, here we have glimpses of the world's first pure mathematics, because the scribe knows that there's the concept of divisibility, right? So he's just left it out. What have they done instead? Can you tell me? What the heck is this?
Not divisible.
We'll go,
Venkat?
we'll just leave it. Yeah.
Yeah. Venkat, you want to answer that? Okay.
Any ideas? Okay, I'll keep talking.
Advai?
I think that extra symbol is not. So 7 is not divisible by.
Okay.
I think it's the remainder.
Interesting. Okay. What is this number?
It
1?
could also be a decimal value. It could be a decimal value.
That's very, very good. You're getting close, right? So in fact,
Or it could be a fraction.
Exactly. This is what we have. This is saying 7 is not divisible into 60, but what is divisible? This is the number 7 and 12. 7 and the next number is 12, and we're going to read that as the next successive sexagesimal place, which is a fraction 12 over 60. Now, if you divide 60 by 7 and 12 over 60.
It's same as 7 over 1 by 5.
What is 1/5 in sexagesimal numeration? 1 over 5 is what over 60?
12 over 6.
1/5. Okay, so we've got 7, 12. Yep. So what if you take 60 and you divide 60 by 7 and 1/5, what do you get?
Jivitesh?
Sir, I think 60 divided by 12 minus 7 is 12. Hence, in the right side, it is written 12. That is 20 minus 8.
What we want to do is we want to, what's this number here? Tell me what this number here is.
Is it 800?
20 minus 8.
820. So
20 minus 8.
Okay, that could be, but is that going to help us? Remember, if we're thinking each successive group of numbers is a successive sexagesimal place. So this would be 8 plus 20 over 60. That's otherwise known as 8.33333333, right? 8 1/3. So 20 over 60 is 8 1/3. So how do these two numbers relate? If indeed somebody very smartly said this is something to do with division, how would we explain these two numbers?
Is
then?
that a mixed fraction? 60 over 7 is converted into a mixed fraction. That's 820 over 60.
Or is it equivalent fractions?
Can somebody grab a calculator and take 60? We're just going to convert. So
I
this
think it's
number
going to
is,
be multiplication of them two is equal to 60.
there you go. So if that's another way, very good way to think about it. If you multiply 7 and 12 over 60 by 8 and 20 over 60, what do you get?
Can you please repeat it? I couldn't hear you.
I'll go to the next slide. Hold on. Here we go. What we have here, so you're very, very right. So we've got a third, its third part is 20. Its fourth part is 15. Its fifth part is 12. Its sixth part is 10. Now, what I am going to do, because we're all like feeling rather anxious without our precious little decimal point or absolute value marker, is I'm going to use a semicolon to say this is my sexagesimal placeholder. So 7/12 you read as 7 plus 12 over 60. So in fact, if you take 60 and you divide it by 7 and a 12th 60s, you'll get 820. Perhaps we'll look at the next one. If 7 with a 30 over it, here it is here, 7 with 30 is another way of saying 7.5, all right, because 30 over 60 is 7.5. If you divide 60 by 7.5, what do you get?
We get 8.
8.
There you go. Good, exactly. And then we've got the next line. So just take 60 divided by 7 plus 12 over 60, and you'll get 8 1/3, 8.333, otherwise known as 820. So in fact, here we have, you're right, it's absolutely right, it's a division table, but it's what we call a reciprocal table, all right? So it's actually giving the reciprocals of number in base 60, because what we have discovered about arithmetic in the ancient Near East is they don't divide very well. And this is the perfect example of right at the beginning of mathematics of that wonderful phrase that I'm sure your maths teachers always throw at you. Mathematics is all about reducing the problem to one that you know how to solve already. So instead of trying to figure out a new algorithm for division, they they reduce division into a problem they already know how to solve, that is multiplying by the reciprocal, all right? So if you want to divide by 2, what you do is multiply by 30 instead. If you want to divide by 3, you multiply by 20 and the like. And I'll let you think about that one for a little bit while I just talk about, so here again, this is probably a student copy, because look, we've got our 8th part is 7.5, and then the student has actually accidentally repeated its 7/30th part is 8. So, you know, I'm sure you've all copied stuff out and repeated things by accident, right? So, and then we got to its 9th part is 6/40, its 10th part is 6, its 12th part is 5, and its 15th part is 4, and so forth. So you will see the numbers that don't divide nicely into 60, that is, have some sort of terminating sexagesimal fraction, are not included. So we don't have 11, we don't have 13, we don't have 14, and so forth and so on. And you can keep reading all of these here. So these are what we call as a reciprocal table. So this is our division table. You are absolutely right. You've got it. That is the way in which we divide something instead is to multiply it by its reciprocal. So if you want to divide something by 2, you multiply it by 30, and so forth and so on. So in addition to all the multiplication tables that student scribes would be carrying around, they'd carry around a reciprocal table. And what I want to say is, you know, this is this table. In fact, there are some, you can see that we're actually dealing with physical artifacts here, which are, you know, 4,000 years old, right? And so do you see these lines here, or these dots here? This is where the actual cuneiform tablet has been damaged and you can't read the numbers. But the fabulous thing about reading ancient mathematics, which is why I just love it more than anything else in the world, is that because of the inherent logic in mathematics, we can reconstruct all the damaged text, right? Because we know what it probably must say. So this one, for instance, we've got 16. So its 16th part is, you know, we've got 345, and this will be 18th, and we've got its 20th part. So you can actually reconstruct the missing text because of the inherent logic of mathematics, which you can't do in any other field. If it was philosophy, poetry, you'd have no hope of reconstructing tablets.
There's a question. Yeah, go ahead.
Ma'am, why do they use different symbols for 9, ma'am? Like in the multiplication one for 9, we saw like there were 3 lines, ma'am, but here it's like there are 2 lines, like the bottom one has a 4 and the top one has 5, but there was like 3, 3, 3. Why do they do like that, ma'am?
Excellent observation, and you're a very good paleographer. You're very good. So this is, you know, this is because mathematics is inherently a human activity, right? And so there are different, just like in Hindi, you write your numerals in one way. In English, we can write them another way. This is to do with, you know, regional trends of how you actually write numbers. It's a very good observation that you've made. And this sometimes allows us, because again, nobody says this was written by blah, blah, blah in this date, so we can't date it. But what we can do is look very carefully at some clues to be able to group text together depending on how they have actually written the numbers. And this is what we would say is probably a Neo-Babylonian, a slightly later text, because it's broken with the canonical 333 for 9 that we see there. So it's an excellent observation. Yeah, and there's lots, so you can see even beyond just the fun mathematics that you can do, discovering the patterns, there's so much more you can say about what was probably going on in these mathematicians' minds as they were writing this and using it. So we'll keep going, and then of course, so I'll tell you, so you can just keep going through and you can see this lovely divisibility. You get up to 54th, the reciprocal. This is wrong, it should be 112 here. You can have a wee look here. And it goes all the way down. So it's 81st part, if you like, is this long string of sexagesimal numbers, but it's still a regular number, still a terminating sexagesimal fraction here. So we read this as 44 over 60. Here it is here. See if you can see it, right? Let's have a look. It's 1/21st part is 44 24, 26, and there's the 40 down the bottom there. So really, again, it's really the joy of reading mathematics is mostly you have an idea of what you want to find, so you can see how you can pull it apart and read the numbers there. All right, so that is that, and you know, you can also cheat, and there's you can look online for using modern sexagesimal calculators there to be able to compute things, but we won't look at that. Right, so now I'm going to look at 20th century mathematics, but 20th century on the other side of the Common Era. And what we can say, most children didn't go to school, so actually mathematics and being literate was the privilege of just a handful of children who would grow up to become professional scribes. All right, here's another one. This will be the test of the day, and it's not many, but I will point out, here's a lovely cuneiform tablet that you can find, and it's a circle, and it just would fit in the palm of your hand, so that's the size of it. And you can see here, so we've got some, what I will tell you are numbers here, and we've got a diagram. So that's maybe a little bit of a clue as to what this is about. But this is very sort of, you know, forensic science here, because if you can look very closely, you can see we've got a fingerprint here. So we could probably say something about how old the individual was who did this, if indeed this was their fingerprint. But this is a trace of a human being doing some mathematics. It's really exciting, right? And in fact, probably when we've got the technology, we'll be able to reconstruct what the person looked like just from their fingerprint. So and get a glimpse of this. But I want you to take maybe, again, 60 seconds, 120 seconds, let's count base 60 here, 1 semicolon 21 seconds to be able to have a look at this and see if you can figure out what's going on here.
May you have a question or the answer?
Yeah.
May, is that a question or the answer?
I have the answer. I think it is a square whose side is given and the diagonal length is written.
Excellent. So yes. So what's giving it away is you very rightly used the clue here, is that we've got a square and we've got the diagonals on it. So this is looking pretty suspicious, right? That it possibly might be a length of the diagonal. All right, so what you can do, so let's try and confirm this. Do you want to, since you're there, do you want to hazard a guess at what the number might be? You want to try reading off? What's this one here, somebody?
30.
30. All right, so we might hypothesize that this is the side, right? So 30. It could be 30. You could think of it, if you like, as a half, or 30 over 60. You also think of it as 30. It's all relative. Right, who wants to bash through this one? Who wants to have a go?
The first one seems like 1, then there's 20, and then there's 4, I guess.
Yeah.
And then there's 5.
That's
No,
50,
that's
I guess.
actually,
That's
50,
50.
I guess. That's 50.
Yep.
Yeah, that might be.
Yeah.
That might be 5.
Yep. 1. And then a 1, yep. And then
1, then 10.
That's
okay. And you can see there's no you could absolutely read this as 20 and then 4, but you could also read it as 24. How can we figure out? Let's see if the next number will help. Who wants to have a crack at this one?
Shall I? First is 40.
40.
Yep.
That's 2 and 20.
Yep.
That's
So 5.
5.
5.
Yep.
30.
And again a 5.
Another 5.
Yeah. Now, if we had all the time in the world and, you know, we were sitting around together doing this in live time, I'd work you a bit harder to try and figure out what those numbers are. But I'm going to just tell you that, in fact, these numbers here are, you read them as 1, 24, 51, 10. And then underneath, we'll read this as 42, 25, 35. And as you've rightly said, it's probably the square. This is in fact, this number here if you take 1 and add 24 over 60 plus 51 over 60 squared plus 10 over 60 cubed, you will get this value here if you write it in decimal. And similarly, half of this number, so if you were to add this up, which helps us actually figure out that this is 24 and not 20 and then followed by 4, you will get this value here as well. Now, if you compare the calculated value for the square root of 2, it's remarkably accurate. So what's the relationship between these two numbers? You might say, okay, this looks like the square root of 2, but how does that fit in with this 30 up here? And how would
Ma'am,
they
maybe they meant that the length
It's
of the
a 30
diagonal
over
will be
60.
Yes,
It's
ma'am.
30 over 60. It's 0.5.
Yep. So very nicely, yep. This is in fact the best 3-place sexagesimal approximation to the square root of 2. So in fact, just doing some modern number crunching, if you take 1 on either side, if you just slip that down to 9, you'll get this. And if you slip it up to 11, you'll get this. So it's the best 3-place sexagesimal approximation to square root of 2. But not only that, why do they care about these two numbers? And this is where context jumps in. Okay, so suppose you've got a side which is a half or 0 semicolon 30. Okay, so just using Pythagoras, you've got the length of the side is 1 over the square root of 2, which if you rationalize the denominator there is the same as square root of 2 over 2. So not only is this length the square root of 2 over 2, but it's double, that is 124, 5110, is its reciprocal. So this cuneiform tablet has a reciprocal pair, all right? So we know that this fits in just in a very nice contextually way with the reciprocal table that we saw. So in fact, this is a very special table because if you want to divide something by the square root of 2, you can multiply it by the other number because that's the reciprocal. So this is probably the reason in which this was investigated. But of course, really interestingly, for those of you that know the Pythagorean theorem is called as the Pythagorean theorem, this cuneiform tablet is no doubt at least 1,000 years before Pythagoras, all right? And so, you know, this is why I don't call it Pythagoras's theorem. It's not his theorem. I call it the Pythagorean theorem, the theorem that is now known as the Pythagoras's theorem, because it was known much earlier. So very, very, and in fact, the next question that many of you are probably asking is, how on earth did they come up with a very precise method? And I wondered, does somebody, if you've done enough advanced level calculus, some of you might have, if I was to ask for you how to compute the square root of 2, how would you do it using calculus? Does anybody know? How would you actually compute? You might do it by trial and error, right? But does anybody actually know the technique?
We will do that
We would do
square
it
root
with
method.
a kind of division method, like we would consider the numbers on the decimal side to be regular numbers, and then we would write the nearest square root, and then we used to collect the remainder and take the other digits of the decimal value and then consider it.
Yep, so you could absolutely do it like that.
I would not use calculus. I would just use the continued fraction.
Yep, that's a way you could do it. But in fact, some of you might have come across the Newton-Raphson method to solve. It might be a little bit advanced yet, but in fact, it's basically a similar approach in which falls out very nicely, although you've got to do it in base 60. So the question that we have as historians is not just what do the numbers say, but what mathematics is implied behind the numbers. Okay, so you see often we just have the computations themselves or the answers. We have to reconstruct the plausible techniques that they actually found these very precise and very accurate figures. Right, I'll just, I know I want to keep some time for questions, but I'll just do a tiny bit of geometry. If you were to, in fact, we could try this. If you've got a scrap of paper, I don't want you to overthink this, but just draw me a triangle on a piece of paper and then hold it up on the screen. if you're happy to share your screen. Just don't think about it, just draw a triangle. Who can draw me a triangle and hold it up if you've got a piece of paper? And Vinay, if nobody's got a piece of paper in front of them, you're going to have to do it.
Oh, no, they are doing
Oh,
it.
there we go. Very nice. Okay, so I've got Dirav, you've got this lovely triangle here. We notice it's got a right angle, right? Yeah. Anybody else drawing me a triangle? Yep, one will do. That proves my point beautifully. Oh yeah, there you go. It's looking very equilateral. Now, so what you might do is if you go on Google and have a look, of course, we've got a nice right angled triangle like you showed me. We've got these lovely equilateral triangles. Beautiful. You're absolutely giving me the right answer. Now, triangles in ancient Near Eastern texts and ancient Mesopotamia, guess what they look like? They have very different orientation. Almost every triangle that we see in ancient school tablets have the orientation with this vertical axis here. To actually say, you know, you think a triangle is a triangle, but actually the way in which we do geometry is to some extent socially constructed, right? So our triangles, all the triangles that you are used to thinking of in your brain when I tell you think a triangle in modern day, you know, in the modern world, they're either equilateral, they'll have a horizontal base, the axis of symmetry is usually vertical, or you will draw me a right angled triangle. So all of you did this. But if we were to ask an ancient Near Eastern scholar or student to do one, they're elongated, they've got a vertical base and a horizontal axis of symmetry, and they're usually right angled. If they are right angled, just like the last one, they will be hanging like this. So very interesting, a triangle to see the social ways in which triangles were conceived. Here's another one here.
Sorry, Clemency, there
Yes.
seems to be a question or a comment. Would you like to take it
Please.
now or? Yes.
Please, yep. Yep.
Yes, miss. Miss, can you go back to the triangle slide, like where you showed the tablet with the triangle?
Yes.
Yes, miss. Miss, I don't know, but like if we see the triangle, there are several triangles in it, and they appear to be similar to the bigger triangle, all of them.
We'd have to look at this in more detail, this particular tablet, to be able to figure out what's going on. Yep.
But by just looks, it looks to be similar, like all of the smaller triangles in them.
Yep.
They look similar to the bigger one.
Yep, that's a lovely observation. Yep. Yep.
Miss, do you
Yes.
think this type of triangles have anything to do, because this is quite old, you know, they used to use arrows and all. So if you take the topper shape of an arrow and cut it in half, then you'll get somewhat a triangle like this, right? So do you think it may have to do something with that?
Well, absolutely. So that you asking the exact question a historian would ask. Why did it come to be that triangles were conceived of that? Just like we might ask, why on earth do we draw equilateral triangles or right angled triangles? You know, where did this actually come from? Maybe it was some feature in agriculture, maybe. And so if we go to the next slide and we look at circles, when you think of a circle, we think very Euclidean. That is, we think of a center and a radius. There are most of the circles in the ancient Near East are conceived of not as a center and a radius, but in terms of a circumference, okay? Almost never do we say, what is this, you know, try and figure out a circle by its circumference. We are programmed to think about the scale of a circle in terms of its radius. For those of you who are very keen here, you'll see there's the number 3 here, the number 9 here, and the number 45. And so the trick is, what are these particular parameters and how do they do with a circle? But we're running out of time, so I'll leave that there as a bit of an exercise for you to play with. But certainly lots of geometrical shapes. Yes, Vinay, please.
Would you like to take more questions now or keep it to the end?
I'm almost finished, so then I'll take lots of questions. We can go through the slides.
Sure.
All right, so just the last thing, just to talk about the different shapes that we might see with our mathematical lens on. Here is a particular school problem that students 5,000 years ago would have had to solve. And it says, the side of a square is 60 rods. Inside there are 4 triangles, 16 barges, and 5 cows' noses. No. Can you look and see if you can figure out what a barge looks like and what a cow's nose looked like. See if you can see this.
Cow's nose is the dot.
Is a barge like when a circle and then there's a dot? I don't know what the weird thing.
That's right. So look at it. You know, whatever a barge is, there are 16 of them. And in fact,
like
what we
that might be a barge. That might be a barge.
Yep. So in
Miss,
fact,
I
what we
think
do,
there are small squares in the bigger square, if you
Yes,
see
ma'am.
very
I
nicely.
think
So there are 16 of them. So that might be a barge.
Indeed. And what we can do as
And the cow's
historians,
nose may be the dot.
Ma'am, the
here's
cow's
a
nose
barge.
may be the top.
Here is some art. Here is some of what we have left over. This is a barge. It's a form of a boat. Does that help us see that? Indeed.
The petal-shaped.
There you go. And what about the cow's nose? Who can see that shape? Do you see the cow's nose?
So it's kind of that floral design thing.
That's exact. So here's our cow's nose. So why are there 5 of them? Here's one, here's another one, here's one in the middle, here's one, and here's one. So these are the cow's noses. There we go. And those are technical mathematical terms for shapes. They didn't persist in the modern day, which is a bit sad really, because they're quite a nice descriptive way for the shape. And anyway, so I'll just, before we get onto all the questions and we can look at all the different details that you've noticed, students haven't really said. So we do have some texts which talk about what it was like to be a student. And this is in a cuneiform text that says, "My little fellow has opened wide his hand, you made wisdom," just move this, "enter there, you showed him all the fine points of the scribal art. You even made him see the solutions of mathematical and arithmetical problems." So there we have it, a father thanking his teacher for helping his son not only be able to write, but to find the solutions of mathematics and arithmetic. And that is something that hasn't changed since 5,000 years ago. The value of education, and may you continue to find all the solutions of mathematics and arithmetical problems, not just the ones that are written in cuneiform. All right, I will wrap up there very happily, and I will open the floor for questions.
Hey, wow. Okay, so we'll take questions. I would request people to make it short and quick. I'll call out names and then you can ask. Miruna. Okay, Siddhi.
So kind of a personal question or something like that. I know 4 languages and I'm learning Sanskrit at school. I take pride in knowing 4 languages. That's pretty rare in the group of friends I know. But how do you manage to learn so many languages, and do you have any tips for learning more languages? And I'm very interested in learning 2 or 3 more languages.
Oh, fantastic. What are the 4 languages that you learn, that you know?
So my mother tongue, I have a mother tongue and a father tongue. So different languages. So I know Marathi, I know Kannada, I know Hindi, and I know English. I'm learning Sanskrit at school. I want to learn German and I want to learn Korean.
Oh, fantastic. Well, I would very much encourage you to do all of that. I think the secret is, if you really, my motivation is I really feel very passionately about trying to read these texts. It's, as you know, mathematics can be quite scary for some people, and a lot of people who are proficient in languages are quite scared of mathematics. And so they look at ancient mathematics and then they're like doubly scared. And so for me, it's really the motivation to be learning these is really to be able to uncover these really important tablets, some of which of course are decaying from the age of time. And I suppose that the trick is that with technical mathematical texts and languages, you learn you learn very quickly the technical vocabulary. So a lot of the texts that are, I'm very fluent in reading mathematical texts, but when I have to read, I don't know, say a literature text or other thing, I'm a little bit slow down. But a lot of the features of languages, I'm sure you know, being multilingual, are common to languages, and it's just a matter of remembering some of the differences between them. So yes, keep learning them, and especially Sanskrit. There'll be lots of work for you to do if you love mathematics and want to combine the two.
Thank you.
Thank you. Sai.
Yes, sir. Hello, ma'am. My question is, what? So I've looked at a little ancient texts like Leelavati and so, but I found that all the questions in there are practical. Like they have some motivation behind them. But the question you just showed us before, the one with the cow's nose, what might have been the motivation behind it, or was it just for purely for solving purposes? Like a pure mathematics question.
So yes, there have been so a lot of these seem quite practical. You're right, and a lot of that's because I've chosen quite easy mathematical tablets, so we could appreciate them quite quickly, or I've chosen ones that are part of a education that would be used in a school. So we do have evidence, though, that this is the world's first pure mathematics. We've got some tablets which are which have the mathematical structure of being Pythagorean triples, for instance. We have some tablets which are big divisors, which have no seemingly practical importance. We have cuneiform tablets, and even the square root of 2 tablet, right? I mean, that's evidence of pure mathematics, really, because why would you even need an approximation to the square root of 2 that was that precise? If you were measuring a field, I mean, come on, you know, you would round up the answer, right? And so this is an example, I think, of this real innate human virtuosity in mathematics to actually push the boundaries of what can be applied practically and get into the pure domain. So you're right, we see, you know, very practical stuff. The Leelavati too, of course, has these wonderful practical problems. Well, they're kind of practical. I mean, you know, some of them are like, you know, there are peacocks in a tree, and there are other, I mean, you know, when are you ever going to, you know, need to figure out the number of peacocks in a tree? But underneath the techniques, they're really, that's almost a feature, a design feature to make them exciting and enticing and interesting and build a story around it. But underneath, particularly for Bhaskara, who's an, you know, incredible mathematical genius, there is really sophisticated mathematics, sometimes, you know, iterative procedures or interpolation going on, or really sophisticated calculus type techniques that's underneath that layer. So you're right. Sometimes if you just bury a little bit below the mathematics, you get this pure mathematics, and we see that as early as the ancient Near Eastern culture. So thank you for your question. It's a very good one.
Also, could you please stop sharing your screen so that we can see you on full screen?
Oh yeah, okay, here we go. Oops. Let me see.
Aditya.
There we go.
Aditya Medni, you have a question?
Yes, ma'am. I just wanted to ask that what is your basic goal behind just finding all these things which happened in past, and how can you relate them to our present?
Yeah, it's a very good question. So really, I think we're talking about the scientific heritage of you know, who we are today. So many mathematical, you could almost say many mathematical insights like Fermat's last theorem, or, you know, modern day proofs, have actually come from people looking at past mathematics in a slightly different way and trying to make a proof. So all throughout history, there are examples of mathematicians getting insight from their predecessors and building upon them and doing something interesting. But I think more historically, we're really talking about scientific legacy of humanity, which is incredibly important to preserve. It's a source of national pride. It's a source of our history. It's what we've learned. And also in terms of teaching, it's really a lovely way, you know, many of you just love mathematics because you just love mathematics. Some learners of mathematics don't feel attracted necessarily to, you know, a typical algebra calculus textbook. And actually, if you can tell mathematics in terms of the story where it originated, it can be a very powerful tool for learners. So I see it as a very useful pedagogical technique, as well as just being sort of a preserving of the past. Yeah, it's a very good question.
Thank you. Next, let me call Haran Mauli.
I have somewhat of a two-part question. So, like, we have many different systems of expressing numbers, just base 10 and base 20, and even the Roman numerals are like a 2 and 5 combination. All of these are somehow motivated by some combination of feet or fingers or something. But the fact that the civilization used sexagesimal system, I mean, in hindsight, it seems pretty smart because 60 has a lot of factors. Yeah. So, but how did they come up with it when they were only first finding a way to express numbers? They should have some sort of mathematical knowledge before that. So is there, the second question is that before we have all of this written documents, is there any sort of historical evidence on how oral communication of mathematics might have been?
Oh, yes, that's the tricky one, right? What is oral is lost for us forever. No tape recorders back in those days. So I think there are some explanations that historians have come up with for base 60. And some people have said, before there was a true centralization of society in Mesopotamia, that there was some, tribe that counted in base 12, there was another tribe that counted in base 10, there was another one that might have chosen base 5, and at a certain point, somebody in the center said, we need to be able to do maths with each other. Let's choose a base which is easy to convert for all of them. I decree that from now on, everybody's going to use base 60 and convert. And so that's sort of in retrospect, that's a hypothesis that some historians have had about where base 60 might have come from. Because, as you say, it's a fairly arbitrary measure. Some people have said, okay, if you count your fingers and then you count the knuckles and then you count the interstices between your fingers and then you throw in your knee and maybe your toes as well, you might get up to 60 if you count your various body parts, and that would be a way to do it. But I think that's fairly speculative. So all we have is the cuneiform tablets that we have to be able to reconstruct where base 60 might have come from. And it might be to do with how many sheep was in your typical flock. I don't know. All of this stuff is, we don't have historical records for this. Yeah.
Is there evidence of like other base systems used before, like around the same area?
There are some evidence, but it's overwhelmingly base 60. Yeah, overwhelmingly base 60. Other cultures of inquiry, Pacific Island, Melanesians, I know Maori, the indigenous culture of New Zealand, had a vigesimal system, seemingly counted in base 20. That's got a nice physiological explanation, right? Your fingers and your toes. Mm-hmm. So how we count is not this sort of fundamental given. It's very much culturally determined. And the minute we start talking about mathematics being culturally determined, I'm going to make some of you very nervous. Yeah, that maybe we could do mathematics otherwise. Maybe in 1,000 years' time we would have thrown away x's and y's and sines and cosines, and actually the way in which we do mathematics might change because we actually change the way we express it, and that will change the way that we conceive it. Really interesting question. Yeah.
Let me see. There are so many hands raised. I really feel that we are short of time, but it's almost 5. Do you have time to take maybe 2 or 3 more questions?
Certainly, absolutely. Okay.
Because they have another session, immediately after this, and there was one more session which got spilled over, and then So let me just call up a few names, guys. Others, just pardon me. Ashwath.
Right. So we've seen that they had quite a lot of stuff written down there, but was there any historical tablet or any sort of evidence found which told us something that we did not know when we found them? We've seen that they gave us the square root of 2, but we knew what square root 2 was when we found it. Was there something that was there something new that we found there?
That's a really interesting question. Nobody's asked me about zero. Nobody's
Because
asked
zero
me
wasn't
about zero.
invented yet, so that's what.
Okay, I'll turn that one around. In base 60, do you need zero?
We absolutely do to differentiate 1 and 60, I guess.
Does somebody wait a minute? Did you see a differentiation between 1 and 60? You've certainly seen a 1 and 60. What was different about it? Where was the zero? Yeah, so it's a very interesting question.
The zero was not actually present in the 60, the letter for 60.
You're exactly right. Yep. Remember, we don't need a place holding zero, okay, because we've got a symbol for 10 and for 1. Yep,
Plus,
so
because there are 16, it's like 16 many texts. We can't say that in this text the student did a mistake. He didn't put a zero because there are many other texts also. So you can't tell all of them did a mistake.
Yeah. So, so when people say zero wasn't invented yet, maybe, but there wasn't really a need for a place holding symbol. As you saw, spaces did the work of telling you successive sexagesimal spaces. But in fact, there's a much more complicated answer, but maybe if I get invited back for another session sometime, we can just look at the history of zero because it's very interesting.
Yeah.
But now maybe you can, one more question. Yes.
Yeah, one more question. Okay, let me just one second. Ananya, can you wait?
Yes,
can you wait? I just want to give a chance to somebody who hasn't spoken yet. Sarah.
Good evening, ma'am. Myself, Sarah. Ma'am, actually, I've known a bit about ancient maths, and since I went to some historical places, ma'am, I've seen that on some of the manuscripts there are some diagrams which actually do not make sense. So, like, is there some relation of the diagrams with the text which are given in this? What do you say? In that particular tablet, or
Yeah. So you're right. Sometimes we are just busting our head because we can't make sense of an ancient text. There's just, we do our best. And as much as we want to say that ancient person didn't know what they're doing, I'm sure the fault is ours for not understanding, right? Almost always, though, particularly with mathematical tablets, if you've got a circle, if you've got some numbers, you can say, okay, one of those has got to be the circumference. One of those must be the area, and you can say, so most of the time, the diagrams will be a huge help and fall very nicely with respect to what they are trying to tell us, just like modern mathematics today. But you're right. Sometimes there are secrets which remain unanswered. The problems are much, much harder. The numbers seem to make logical sense, but what they apply to or how they relate to one another or just a general problem remains forever hidden by the mists of time. So yes, those are the most fun problems.
Ma'am?
Ananya.
Yes.
Can
Ma'am,
you?
so
Who's that? Ananya. Wait. There are people.
Something is in my mind, and I wanted to just tell it out.
Okay. It's a comment, not a question, is it?
Yeah.
Okay.
So since we knew a few theorems, we were able to find out what they were trying to tell us by those scripts. So if something is not, if something is there and we are not able to find it, does it mean that like there is much more for us to find? Like they have found something more than us, but we are not able to find what they have found.
Yep. So that means sometimes, and it's the same with ancient Greek mathematics written in Latin, mathematics written in Sanskrit. There is some stuff that we just don't understand or can't provide context to as modern scholars. And sometimes it just takes a matter of time you know, really applying yourself, just like a modern mathematical problem where you just really need to sit and stare and think about it and come back to it and go for a walk and come back to it. Sometimes this happens over a matter of weeks or months or even a year. Sometimes we find other sources which help explain the particular thing that we do, and that's a real pleasure. But yes, sometimes things can be explained, and sometimes we just just have to keep applying ourselves to the problem.
Okay, so I'm going to put a hard stop now. So, yeah, I'm sure all of them have amazing questions. I'll, before I invite one of the participants to share her feedback and give a vote of thanks, I just, had two questions which I think will be very useful to bring here. So one is, if you can just share, what do you think these guys, I mean, all of them seem equally interested about history of mathematics. Perhaps many of them are exposed to this topic probably for the first time in their life, right? So what do you think students in India, especially if they want to learn more about history of mathematics, what they can do? This is one. The second is, what about learning, say, languages like Latin or Greek, or learning about these cuneiform tablets? How is there any sources from where they can learn while they are studying in India?
Yeah. So yes, history of mathematics. So of course, and often we think about history of mathematics, we think of some really great names like Newton and Leibniz, and names that you might, very famous Western mathematicians. But my goal is to actually say there are mathematicians, Ramanujan, for instance, and Bhaskara and Aryabhatta and Brahmagupta, and Chinese mathematicians, all of whom, made equal and interesting contributions. So I would say, I think, there are some books that you can get called History of Mathematics, which is a nice place to start. There are lots of, maybe I can send you a list of, podcasts and short YouTube clips that you can look at this. Maybe some schools and universities will have a course in History of Mathematics. They're becoming a little more popular. And so yes, and go back to the sources. It's all online now. If you're interested in Newton in the beginning of calculus, just go get the Principia, right, and try and have a look at a translation. It's very exciting. You can find it all online now. Similarly with Bhaskara's Lilavati, there'll be lots of translations that you can get online. Go and have a taste of it. And so yes, learning. So for Sanskrit, I would really encourage you. There's mountains of original material in Sanskrit that's yet to be read, and it's right at your doorstep. So that's an obvious one for me. And there'll be classes, spoken Sanskrit classes. I know some that are in Australia and New Zealand. To learn some Sanskrit, you'll have a natural advantage, probably those of you that have got related languages. But Latin and Greek, there are probably online study resources that you can find for that too. But just I learned through textbooks and courses, but you'll no doubt teach yourself courses online. So I would really encourage you, and particularly, as you can see when you read the mathematics, you have a sense of what it must mean before you read it. So you've got a natural advantage if you're reading a topic in mathematics, particularly if there are numbers, because they'll help you put the words together and get the meaning out of it. So it's a very great inducement to read a foreign language if you're trying to read a mathematical text as well. Yeah.
Thank you so much, Clemency. I would like to now ask Sai to share a few words about how did she feel about the session, and then we'll close.
Thank you very much. It was a wonderful session. I enjoyed it a lot. At first, when I heard that this was going to be a session on history, I wasn't sure what to expect, but it was such a wonderful session, and now I feel like a mathematical historian, and I'm pretty sure thank you so much for inspiring all of us to study more to study the history and how far we have come. I love the session, and I wished we had more time and we could do this face to face.
Very
Thank
good.
you so
Well,
much.
I'm delighted to be able to share a little bit of my passion with you, and perhaps we can, I'll come back for a repeat session. We'll do some harder Q&A for mathematics. You can have some fun with that. Yeah.
I'm sure, and probably when you come to India next time for doing a workshop, maybe some of these guys can join in, maybe in IIT Bombay or Madras, wherever you do,
Yeah.
right? So
Fantastic.
yeah.
Yeah.
So thank you so much once again. From our end, Clemency, it was a wonderful session, and I really wish we had more time. So probably we'll do a workshop on history of mathematics for kids sometime.
Sounds wonderful. Sounds brilliant. I'll be in. I'll be signing up.
Excellent.
That would be
Thank you so
wonderful.
much. Thank you so much. I know how pressed you are with time, and still you took out time. Really appreciate from the bottom of our heart. So
My pleasure. And keep studying hard, and remember, just keep alive the effect that mathematics is not just logical and analytical. It requires lots of creativity and imagination as well. So I think if anything, keep that at heart. All of you are intensely creative young people as mathematicians. So nurture the creativity in you as well. That's how you'll discover things we don't know yet.
thank you so much for those inspiring closing words, Clemency. We really look forward to have you for one of the later sessions as well, probably when we do face to face. Yeah. Thank you so much.
Okay. Take care.
Thank you.